We're going to start with Dr. Alpan Raval first. Our first speaker is a chief AI scientist at Vadvani AI Institute. It's a non-profit organization, and he's going to talk about AI for social impact. Please welcome.
Thank you for the invitation. I have to apologize in advance because this talk is going to be a bit different from what you've seen so far, in the sense that it doesn't contain anything molecular at all, but I hope to convince you that there are interesting applications of AI in biology beyond molecular applications. So just a bit about what we do. Let me see. Yes, okay. I think most of this audience knows what responsible AI is. Usually it's about applying responsible practices and techniques to existing AI models, either as a layer on top or integrating them within model training itself. And it includes things like debiasing, privacy protection, human in the loop, and so on. On the other hand, there is a responsible use of AI, which really constrains the application domain. So as an extreme example, it wouldn't make sense to have AI for the military that is responsible, right? I mean, at least I think so. So having, for example, weapons design be fair and privacy preserving and so on, it wouldn't make a lot of sense. So our institute is a nonprofit that focuses on responsible use. Our charter is building AI for the Global South, and specifically for underserved communities across the Global South. And so our target communities are typically those who don't have access to technology, to internet, have basic mobile phones, but they're not always connected to the internet, and so on. And the question we ask is, how can AI help these communities improve lives, livelihoods, and so on? So it's large-scale social impact that we're after. And our work has so far been restricted to India. We're in the process of expanding to other countries. So I'm going to be talking about two projects today, one in agriculture and one in healthcare. This first project is an agriculture project, and the work I'm going to talk about is based on a few papers that we published over the years. It's still work in progress in the sense that we haven't yet achieved the scale of impact we'd like to achieve, but the models are reasonably good. They're working reasonably well, as I'll show. So just some context. Cotton is one of the largest cash crops in the world. Nearly 90% of cotton is grown by smallholder farmers who own less than an acre of land. And these farmers are typically ones who struggle the most with yield uncertainty. They live pretty much from season to season. They're dependent on the current year's harvest in order to go through the next year, right? And in countries like India, for example, a leading cause of farmer suicides comes from, leading sort of population that goes through farmer suicides is cotton farmers. And this is precisely the reason, because of huge uncertainties in yield and income. So India happens to be the world's largest producer of cotton. It grows 26% of the world's cotton, and more than 75% of cotton farmers in India are either smallholder or landless. 41% of the total farmland in the country is used for cotton. There's 6 million cotton farmers, huge numbers. 40 to 50 million people in all engaged in ancillary activities around cotton. The problem with cotton is that it's particularly vulnerable to pests. And this is a cause of low yield. For example, in India, the average yield per hectare is 480 kilograms or so, whereas the the worldwide average is closer to 750. 30% of yield is estimated to be destroyed in pest attacks. And of these pest attacks, 70% is caused by what are known as cotton bollworms that attack the cotton boll. As a result, nearly half of India's pesticide usage is on cotton, right? And this is bad for the environment. This is bad in all sorts of ways. It's costly for the farmer. It's bad for the environment using pesticides. And they're so scared of pests that they indiscriminately spray pesticide, right? And this is the problem we wanted to see if it could be addressed using AI. So yeah, various consequences of overuse of pesticides. What we built was an app called Cotton Ace, which is an AI-based early pest warning and instant advisory system. It's fairly simple in use, but it solves an important problem. So the problem that it's solving is it helps farmers protect their crops before they are attacked by pests, or before they are significantly attacked by pests. It also helps the agricultural program officers manage these programs well, and it replaces a manual system that has been going on for decades. And the manual system works as follows. So typically there's a lead farmer in a village who installs a pest trap. The pest trap is not really meant to destroy the pests. It's more meant to get an estimate of how many pests there are, right? So the pest trap catches a few pests. They take a picture of the pest trap, and then when they're connected to the internet, they send it to the local agricultural university. The agricultural university looks at the pests on the trap and gives them feedback on whether they should spray pesticide or not. And this entire manual cycle takes a week to 10 days. By the time often the farm is already attacked by pests and it's too late, right? So we wanted to replace this with a computer vision-based advisory. And I should mention this project won the Google.org Impact Challenge Award a few years ago. It also won the H&M Global Change Award, I think 3 years ago. The app is multilingual, works in 9 languages. It's very easy for the farmer to use. It allows inference on edge, offline. It doesn't need internet, and it gives you real-time alerts. So this is sort of what the cotton plant looks like after the bollworm has infested it. And the way, sorry, you can't see video on this, but that's okay. The way farmers use the app is they first install a trap. So there's a demo farm in a village. A demo farm is sort of a representative farm, and it's defined by a farm in which the farmer can afford to have a smartphone and can afford to buy a trap, right? So they install a trap on the farm. Every couple of days or so, they are supposed to empty the contents of the trap onto a piece of white paper. And the image looks like what you see there, the second picture there. This is actually a very clean image. A typical image looks like, there's a bunch of these bollworms, these pests. There's dirt. There's all kinds of other pests. It's all mixed up. And so the farmer takes a picture of that image through the app, and then the app gives an advisory on whether they should spray or not, right? So it's fairly simple. What the model is doing in the back end is it's just counting the number of pests of a certain type, right? So it needs to learn to recognize the pests, and it needs to count them. So at the back end, it's an explainable model in the sense that there are bounding boxes around every pest. So if the model is doing something wrong, it's possible to figure out what's going wrong. And then once this advisory is sent to the lead farmer, then there is, the lead farmer is connected to all the other farmers in the village, and the advisory is then transmitted to all the other farmers, and that's how we achieve scale. So the data for this, it's about 16,000 images that we collected in the field. So the 16,000 images includes data collected from the field and then human annotated with bounding boxes. Data that we received after we did an initial pilot deployment. So we had that data that was again annotated. And then we need sort of negative data, images without pests. And we use the COCO data set, which is a large sort of image segmentation data set that's open source. And what the app does currently is identify the 2 major pests that attack cotton farms. That's the American bollworm and the pink bollworm. There's huge data challenges. Even though the modeling looks sort of simple, there's huge data challenges in this. There's occlusions, there are tiny pests, camera resolution is low, out of focus images. There's lack of diversity in the data, not enough counterexamples. So for example, if the farmer took a picture of a white wall with smudges on it, that can throw off the model, things like that, right? Majority of the pests are small and dark, and that looks very, very similar to dirt, right? And then, there's other sort of data split issues that, we've solved, and then bad annotations as well. So you need expert annotations on data like this. If you take an image like this to a typical entomologist, they're used to seeing images of live pests. They're not used to seeing images of dead pests. So they often make mistakes. Sometimes, single pest is scattered all over the image. So there's huge issues like this. So we had to go through a lot of data quality iterations, modeling iterations to get this right. So these are some examples. On the left, you see an occluded image where you have a whole bunch of pests sort of occluded together. It's impossible even for a good computer vision model to be able to count the number of pests on this. Tiny pests and so on. So I'm not going to go through all of these. And this is what the modeling workflow looks like. So you should really read this from bottom to top. You have input image that goes into the phone. And there's first a rejection model that tells you whether this is a valid image of a trap or not, or whether it's something else. And if the rejection model rejects it, the farmer is encouraged to retake the image. If it's accepted, then there's an identification and counting model that counts the number of pests. And then depending on the output, we also have conformal prediction on top of this. So depending on the output, either the output is accepted, or if the uncertainty is too high, the model abstains from taking a decision. If it abstains, it goes to a better model that sits on the cloud. So the image is then transferred to the cloud, and this cannot happen in real time. It can only happen when the phone is connected to the internet. So it syncs up with the cloud, and then we have a larger model on the cloud that does the same thing. If the larger model abstains, then you have a human-in-the-loop workflow. So that's how we ensure that this whole system is high accuracy. Yeah, so the phone model is based on the YOLO V8 architecture, which is a very popular segmentation architecture, which we retrained from scratch on this data. Actually, no, we didn't quite retrain from scratch. We used the starting weights from training on COCO, and then started off from there. So a bit of transfer learning. On the cloud, we have a much larger version of this model, the YOLO V5, and so that's how the workflow goes. And then we have a rejection model that's also a version of YOLO. So some results, the columns that you see, the MAE is the mean absolute error, PBW is the pink bollworm, ABW is the American bollworm. So the mean absolute error looks kind of high. This is the error in the count. So 3.66 would be an error in the count of the number of pests. It turns out that this error is dominated by the clumping phenomenon that I showed you earlier, where you have pests clumped together. And so if you throw away predictions larger than 20 in computing the error, and that makes sense because if there's more than 20 pests on your trap, you're supposed to spray pesticide anyway. It doesn't matter what the AI is telling you. So if the AI estimates more than 20, if you remove that from the error calculation, then you get this MAE at 20, which is really well controlled. It's less than one count per image. And you can see the phone model is small enough to fit on a basic smartphone, 45 megabytes. The rejection model is extremely accurate. And this is the effect of abstention. The accuracies before, this is the accuracy on false alarms. The accuracy before extension is around 91%. After, if you include abstention in the workflow, the accuracies go up to 95, 96%. So we've deployed this over the last 3 or 4 years in various settings, and then we've measured the effect of farmers using this, right? And I'll just quickly go through the results. I'm aware of time. I want to get to another project as well. We get, farmers who use this app report 17% better yield, 8% better price due to better quality of cotton, and so on. 26% reduction in pesticide cost, 20% increase in profit. And what we've done right now is currently this is integrated into a much larger national pest surveillance system in India that includes both sort of trap-based images as well as images of plants, direct images of plants that are infested. And we built models for those as well. So it's currently being used. The next project I know I have 5 minutes left. I'll spend the next 5 minutes talking about another project that's in progress. This is a healthcare project where we're trying to screen for TB using solicited cough sounds. Right? Again, TB is tuberculosis is a huge problem in India. It has the world's highest TB burden, I think, just because of population numbers. 25% of the world's TB cases are in India, and about 30% of the world's TB deaths. And in spite of these numbers, it's estimated that about 64% of TB cases are just missed by the system because people don't get screened. People, there's huge sort of social taboos around TB. So if they're coughing or if they show symptoms, they don't go and see a doctor. Diagnostic tests, these are typically molecular tests that detect the bacterial DNA within sputum. These are very expensive and therefore not scalable in rural areas in India and Africa. Chest X-ray is a standard screening method for TB, but that's also not very scalable in rural areas. You need large equipment in jungles, in remote areas, and so on. And so screening is typically done through self-reported symptoms. There's the classic sort of 7-symptom rule that people use. If you have these 7 symptoms, then you should go for confirmatory sort of genetic testing for TB. So our long-term aim with this project is to develop a high-sensitivity TB screening rule that can be used in remote areas, that can be used in the field. And so it has to be cheap, it has to be compact, scalable, and this was really inspired by our work on COVID, where COVID has a very distinctive cough signature, as you all probably know. TB does not. So this is a much more challenging problem than the COVID problem. And this is based on solicited cough and self-reported symptoms. So we have some encouraging results. I won't go through all the details. So we take 3 cough recordings per patient, and then the patient sort of reports whether they have one of these 7 symptoms: cough, blood and cough, fever, chest pain, etc. And also if they have any known comorbidities like diabetes or COVID, or if they're alcoholics and so on. And then the model in the back end gives a prediction of whether you ought to go for confirmatory testing. The data collection problem was huge here. It's very difficult to convince random people to go for a TB test, given the sensitivities around having TB. And TB is a very low prevalence disease. I think it's 0.04% or something like that. So you have this sparsity problem. As a first pass, what we did was there are TB health clinics throughout the country. And we went to TB health clinics and collected random samples from patients. And for negative samples, we asked the workers in the health clinics to contribute their cough sounds, right? So that was sort of negative data. And then later, in addition to this data, we also collected data from contacts of TB cases, immediate family members and so on. And then we collected data from individuals going in for a chest X-ray at public health facilities for any reason, right? So we have a mix of these various data sets, and they have very different prevalences of positives and negatives. So it's a very challenging machine learning problem. There's data mixed across different domains, different prevalences of positivity. The facility data had the highest TB prevalence because these are TB facilities. You expect most of the patients to have TB. So roughly half the patients there had TB. On the other hand, the health workers are expected to be mostly negative, so very few had TB. Contacts of TB cases, we got 3% prevalence of TB. And X-ray facilities, because it was general X-ray, again, very low prevalence. Not going to go through a lot of modeling details. Essentially, again, we have We built a cough detector model that detects whether something is really a cough sound or not, and that's a very high accuracy model. And then the model analyzes the cough sounds and the tabular data, the symptoms, and we create an ensemble model that gives an output. And yeah, so the cough detector is very high accuracy with an AUC of 0.99. And then we do pre-processing on the cough. We take the audio recording, convert that to time, frequency, space, do a MEL transformation, so you get what's called a MEL spectrogram. We did data augmentation by masking time and frequency regions, very small time and frequency regions in order to create a larger data set. And a lot of things that had to be done to the data in order to get the model to work reasonably. So I'll just skip straight to the results. We do aggregation across cough sounds. This is the tabular data that we collect. And relative to symptomatic screening, the results are not great. So there's 3 types of models: a cough-only model, a model based on symptoms alone, and a combined ensemble model. And we look at specificity at a sensitivity of 90% and sensitivity at a specificity of 70%. And you can see the cough-only model doesn't do great. And this was discouraging in the beginning, but then what we found is that, sorry, I have to skip a few slides. What we found is that if you restrict the analysis to those who don't have symptoms and are TB positive, the cough-based model does a lot better than the other models. So cough seems to capture some signal for TB that's not present in symptoms. So it's very good at detecting asymptomatic or pre-symptomatic TB cases before they get symptoms. Right. And then we've deployed this in various settings. And what we found is that consistently, if you look at our deployments across time, we consistently find between 12 and 14% additional yield of TB cases due to the cough sound alone. And these are all asymptomatic TB patients. So we think there's a lot of promise in this. We continue to develop it. What we need is further data from community settings and basically asymptomatic TB positive individuals. That's our biggest challenge, getting people who don't have symptoms to volunteer for a TB test. And then, of course, we need to build interpretability around all of this. We want to be able to isolate parts of the cough that carry the TB signal and also be able to map the AI score to the severity of TB. But this is where we are right now. Thank you. Happy to take questions. These are the 2 teams. Lots of people worked on these projects, especially because of deployment issues.
We have set it up Slido, so people joining us online can post their questions on there. So anyone has a question?
Thank you very much for the talk. I was wondering, I'd love to hear your perspective on what you think needs to be improved or changed to make rolling out these models or these sort of applications easier. Is it on the hardware or software side, or is it mainly social, perhaps?
It's mainly data, that much better data gathering systems at scale. It's the problem in these situations is really at the 2 ends of the AI, getting better quality data and having deployment platforms so that you can create impact at scale. The modeling is the interesting problem, but it's easier than these 2.
Thank you.
Just following on from that, you said you had problems with your data annotators. How do you get over that? I mean, bad quality data. I presume it's disagreement between annotators, or?
Yes, so we had to account for annotator disagreements, and we had to hire entomologists to annotate the data. And then we took sort of consensus majority votes on annotators. But there are other ways to do it.
Out of curiosity, what was your inter-annotator agreement?
On the counts, I think on the false alarm. So there's thresholds on the counts. If the count exceeds a certain number, you have you have a recommendation to spray pesticide, and that number varies season by season, and that's computed by entomologists. It's called the economic threshold limit. So if you, I think, I'm trying to remember. So on the final recommendation, not on the count, on the final recommendation, the inter-annotator agreements were fairly high, in the 80 to 90% range. But on the actual counts themselves, they were pretty low, maybe 50, 60%. So, yeah.
Thank you very much for the great talk, Alpan. I was wondering, you mentioned a lot about the data source of the TB being very imbalanced between the negative and the positive cases, which I assume cause bias in your model. I wonder how you're actually going to encourage people to come forwards who potentially are asymptomatic TB sufferers, what the strategy is that you're going to put in place for that.
Yeah, so from a modeling perspective, so far what we've been doing is only training on the facility data, which is 50% positive, and then using the other data sets for evaluation, for hyperparameter tuning and evaluation. Going forward, I think getting normal individuals to do TB testing, we have to piggyback on what are called case finding efforts. So there's prevalence studies that go out in the community and try to figure out what's the prevalence of TB in the community by region. And what they do is they use statistical methods to sample individuals at random and then test them for TB. And what we're trying to do is collaborate with the agencies that do this so that we also capture cuff sounds when they're doing this. But this happens once every 4 years or so. So I think we have to wait a year before we can get that data.
Thank you.
Hi, thank you. I was wondering, one of the boons from the pest control was reduced pesticide use. Are there any measures of biodiversity being maintained or increased through the use of this? And is there any opportunity to gather that as a kind of residue from your images, or are the traps too specific?
That's interesting. We've never thought of that. You mentioned biodiversity, right? No, we haven't thought of that. So, and I don't know if that information exists in the images.
Are the traps too specific? But you mentioned a pheromone.
Yes. So we have trap-specific images, but I don't know if that's going to tell you much about biodiversity.
I'll squeeze in a second one. I was curious how many people, and you mentioned, and you put up a list of people which looked like 30 to 40 people or something like that. I was curious what kind of timescale it took you to put together these things and get to a result.
Yeah, so for the Cotton project, we've been working on it over the last 4 years. The TB project, about 2 years. These are fairly long time scale projects, mainly because of the data collection and so on.
Yeah, it's fine. We can just take one more question, one last question for now, if that's okay.
I noticed on the company GitHub that you've run a couple of competitions to try and make new models. Have you had much success with opening it up to the community and running those sort of challenges?
Yes, so for the Cotton model, we got the YOLO idea from a competition. We were using a single shot detector model earlier, and the YOLO models work a little bit better.
Great, thank you.
Thank you so much.